I've contributed to Python since like around 2016, and I was made like a core developer a couple years ago on this project. So real quick, let's go over the basics of Python. You guys might be already familiar with it, but it's an interpreted language. It's mainly known for like its fast prototyping and really like rich libraries. You have like everything from machine learning to like computer vision to like HTTP stuff. People build like almost everything in Python, and because of the libraries, you usually can work pretty fast on it. A little bit about the history of Python. Python is really, really old. It started actually all the way back in February 1991. So it's actually older than Linux itself, for example. In October 2000, the second version of Python came out. And in 2008, Python 3, which made a lot of breaking changes, came out. And then finally, last year, Python 2 was discontinued. And now Python 3 is the only available version. And I'm not kidding about the history. Because of how old it is, it's really common, for example, for me to do a git blame and find a commit that's from like 25 years ago. And so there's a lot of like baggage that comes with being this old. But it also means that there's a lot of like things that it pioneered as far as interpreted languages go. So now let's take a look at what happens behind the scenes when you actually run some Python code. So the first step is a compiler. But you might be wondering, in an interpreted language, why do we actually need a compiler, right? Like you can just go ahead and parse the source code and just like start running the actual parsed code. That is true, but in reality, what we are interpreting in an interpreted language is not actually the source code of the language itself. So for example, in Ruby, you're not actually interpreting the Ruby code. The Ruby code gets turned into the Ruby virtual machine code, and then that gets run on a Ruby virtual machine. Same thing for Java. You're not actually interpreting the Java code when you run the JVM. You're running a bytecode that the Java code was compiled into. So in the case of Python, there is the CPython interpreter bytecode, which is what actually gets run. And this is, it has like around 100 different opcodes, and the virtual machine is stack-based. So that means if you do something like an add, what it's doing is it's popping off two things off the stack, adding them, and then pushing them back on the stack. So all of the operations are kind of based on this stack, and then like a bunch of dictionaries and stuff for a state. So you might be wondering, why would like interpreted languages add like this bytecode layering? Why don't we just interpret the AST straight away and just start executing the code? Well, as it turns out, if you interpret the AST, as your language grows more and more features, it becomes a lot harder to actually like interpret and fully run the AST. So for example, in Python, there's this behavior where if you have these two functions, f and g, where all they do is increment a number, for example, in Python, all functions will return none at the end, implicitly. So even if you didn't put a return none, once G finishes execution, it will return none. So you can imagine if you were writing an interpreter that was running the AST, you'd have to have like all these special cases like, oh, if I have a function and it doesn't have a return statement, now I want to do a return. Whereas with a compiler, you can compile both these functions into the exact same bytecode, and they will have the exact same behavior. So when you build features, it's a lot easier to just alter the compiler and never have to actually touch the interpreter. And this also lets other languages target your virtual machine. So for example, in Python, there's Jython, which is basically a Java compiler that runs on the Python virtual machine. There's something similar for C#. So you can have other languages target your interpreter if you have like this bytecode layer in between. And also bytecode in general is much easier to optimize. In the AST, you don't have like as much information necessarily as you would in like a compiled bytecode form. So in the case of Python, for a hello world program like this, we can take a look at what bytecode it will actually get turned into. So these are the line numbers on the left side. So as we can see on line number 1, where we assign x equals hello, it's basically just doing a load of a constant, the string hello, and then storing it in the variable x. For line 2, similar thing with y, just load a constant called world and store it in the variable y. And then finally, once those two are assigned, what it does is it loads the print function global. It loads x, it loads y. It calls binary add on them, so this is the concatenation of the strings. And then it calls the function with one argument, the concatenated string. And then this is the behavior I was talking about, where if your function doesn't have a return, Python will implicitly add one in. So it pops the top, which is the print's result, pushes none on there, and then returns that none to the calling function. So when you're running Python, you write this source code, but the first step in actually running it is compiling it from that form into this bytecode, and then that bytecode gets run. So really what's going on behind the scenes is we have a traditional compiler on top, just like you would for C, Rust, like all these like ahead of time compile languages. But instead of targeting the machine, so instead of making CPU instructions, it's making bytecode that will run on the CPython virtual machine. So you have a traditional compiler array on top with a tokenizer, a parser, optimizer, and bytecode generator. And then the last step, it will generate bytecode that will run on the Python version. So the tokenizer generates a stream of tokens. We'll look at these steps in more detail. The parser takes that stream of tokens and turns it into an abstract syntax tree, which is just parsing those tokens, making sure they're a valid program. The optimizer will try to take that AST and simplify it as much as it can. And then the bytecode generator will crawl that AST and generate the right bytecode for each of those nodes. And then finally, once all of that is done, you can go ahead and run that on the virtual. And this step can be, the compilation step can be done beforehand. So you don't necessarily have to compile as you're running. You can have all your Python programs pre-compiled and just run on the virtual machine. So let's look at the first step of this process, which will be the tokenizer. So the tokenizer is taking the source code, and it's really hard if you just have the source code to kind of turn it into the right form, the AST that you need to figure out, oh, hey, this is an assignment, this is a function call, this is subtraction. It's really hard to do that with just the raw characters. So usually the first step in a compiler is to tokenize it. So for example, the X turns into a name token. The equals is an operator token with the value equals. The hello is a string token, and then there's a new line. Same thing for the Y. And then down here, for the print function, we have a name print, and then we have the left parenthesis operator. So the tokenizer will literally just go through your source code and turn it into this stream or list of tokens. So Python's tokenizer happens to be written in some handwritten C. These days, you can find tokenizer generators where you give it a bunch of regex for what your things look like. Okay, I want variable names that can only be A to Z, 1 to 0, and it will automatically generate a tokenizer for it. But Python is so old, it predates most of those tools, and so its tokenizer is handwritten all in C. So if we look up here, what it's doing is it's taking the next token from the next character from the file, and then it's basically a bunch of if statements on that to figure out, okay, is this a variable name? Is this a plus, minus, function call, that sort of thing. So for example, if it sees a hash, which is how you declare a comment in Python, then it will ignore the rest of the line because those tokens don't matter. If it's the start of an identifier, so a variable, then it will do a while loop on all of the characters that come after it, and then it will emit a name token. So this is what we saw earlier with the X and the print. It'll loop over and try to find those. So one really nice thing about Python is that a lot of these steps that I'm going to show you are actually introspectable. You can view the actual details of them through the command line through other Python code. So for example, the tokenizer is actually available in the standard library as the tokenize module. So if I take that test program and I added on a little extra at the end just to show you what that will do, you can literally just run python-m tokenize on the file, and it will spit out the output of what the tokenizer did on that. So this is the output we saw before. This is the internal tokenizer. Just you can run it on any file you want. So one thing that you'll note here is that this is not valid syntax. You can't just put another function call in front of an old one without like a new line, a semicolon, something. But notice that the tokenizer has no problem with it. It took the part that's the print and added on the part that's the second function call. So this is an important part. The tokenizer is not doing any checking on the source code. As long as it will just return a stream of tokens, it does absolutely no checking to see, hey, is this a valid program or not? That will come in the next step. So after we got these stream of tokens, the next step is a parser. So the parser will take these list of tokens and turn it into a tree that's more like logically arranged to represent what the program is doing. So Python used to have an LL1 parser for the longest time, which means it would scan tokens left to right. And in order to figure out which syntax it is, so for example, if it's a function call, it could only look ahead one token. But this limitation was kind of too limiting. So there were a lot of hacks that had to be put into place in the interpreter to support like new fancier syntax. Such as when Python added async and await. People were already using the variable names async and await in their code, but now it had to be part of a keyword syntax. So because we had to make it like a soft keyword that you could still use in your old code, there had to be a lot of hacks added to the parser. So in 2020, we basically decided, okay, the LL1 parser had served its need well, but now in order to simplify the grammar and the code, we're going to switch to a fancier new kind of parser, which is called a parsing expression grammar, or a PEG-based parser. And that made the code and the grammar a lot simpler, and maybe the code of a little performance. So let's take a look at that Hello World example and what the parser actually does to it. So X and Y assignment are pretty simple. So we have an assignment node, and the assignment node has two fields in it called the target and the value. So the first line, the target, is the name X, and the value we're putting it in is the constant hello. And in the next line, we have target, the name is Y, and we're putting in the constant value relevant into it. So these are relatively simple nodes, but let's look at what the print statement actually looks like. So the print statement is a call node where the function is a name called print, and the arguments are actually a binary operator, so the X plus Y. And the binary operator's left-hand side is the name X, and the right-hand side is the name Y. So notice that the nodes don't necessarily have to be like names, constant, that sort of thing. The individual nodes can also be complicated expressions themselves. So if you were doing like print and then you had like an fx, there would be a call up here and then another call down here. So the parser can take like arbitrarily complex programs and turn them into these like nice little trees for us. But so how do we actually get to these trees from our like list of tokens? Well, that is done using a grammar file. So the grammar is basically how the language is structured, like what stream of tokens is considered like what syntax. So for example, if we look at assignment, assignment is a name. So we saw names earlier. Those were basically like X, Y, print, and equals. And then you'll notice that this part is parenthesized and there's a plus. That basically means one or more. So in Python, it's valid to do, for example, X equals Y equals Z equals 1, and that will make all the variables 1. So that part covers assignment. So both of these, X equals hello and Y equals world, are valid assignments because they have a name, X, Y, they have an equal sign, and then they have an expression at the end. So what is an expression? An expression is either a name itself. So for example, you could do A equals B to give the value of B. It could be the booleans, it could be like all of the primitive like types, numbers, lists. I've skipped over like this huge list of what expressions can be. But importantly for our case, they can be strings. So this piece of syntax matches the assignment rule because it has a name, equal, and it ends in an expression. So the parser will look at this and say, okay, this matches assignment. I'm just going to make this an assignment, and then it moves on. And then for the function call, it matches this part, the primary it's called in Python's grammar. So that has to be a name, so in this case, print, a left parenthesis, and then optionally arguments, because you could have an empty function call. And then arguments is either an expression itself or an expression followed by a comma. So this lets you put in like as many arguments as you want into a function call. So just like the tokenizer, the parser for Python is also exposed within Python itself, and it's called the AST module. Because like we said, what it parses it into are these abstract syntax trees. So if you want to look at what your Python code actually turns into when it's gone through the parser, you can run python-m-ast, and it will give you like the actual parse tree that the parser generated. And this tooling is sort of used a lot in the ecosystem. So if you have like a linting tool that wants to make sure like, hey, you're not using like stupid variable names, it can use Python's built-in AST module to parse the source code and like do things like that on it. So once we have a AST created by the parser, the next step is the optimizer, which tries to simplify that AST as much as possible. So if we look at that print again, and imagine that instead of x and y, we have two constants, 10 and 20. The compiler can look at that binary operator on those constants and be like, I don't need to like do these at runtime. At compile time, we already know what 10 plus 20 is. So instead of putting in that binary operator, it literally just replaced the argument with the constant 30. So this is like an example of one of the optimizations Python does. There's not that many because Python is very dynamic, so you can do a lot of things in it that will not necessarily, you don't necessarily know at compile time. So this is why languages like C and Rust are usually better in terms of like how much optimization you can do on the AST. But Python does these small little optimizations wherever it can. And then once we have the simplified AST, the next step is to actually generate the bytecode from it. And so for that, we have basically what's called an AST visitor. A visitor pattern is just where you traverse the entire AST, and you have like these cases for what to do depending on what node you land on. So for example, if we look at the assignment case, what it's going to do is it's going to visit the value, and then it's going to visit the target of the assignment. And so if you remember from our AST from earlier, the target of the assignment is the name x, and the value is the constant hello. So if we look at what it does on a constant, it's going to add the bytecode load const for it. And like we saw in the finished bytecode, there was a load const for the hello part. And then it visits the target, which is a name. And that goes into a helper function called compiler nameop. It does some checks to make sure that name isn't forbidden. So for example, you can't assign to false in Python, true, those sort of things like those constants. So it checks that you're not trying to overwrite one of those built-in variable names. And then once it's done with that, it'll put in like the right opcode, like a load global store, that sort of thing. So just like the tokenizer and the AST, you can also view what the compiler generates in terms of bytecode. We saw this earlier, but if you want to do this for your own Python programs, you can just use the dis or the disassembly module. And this basically just takes your Python source code, parses it, generates the code, and then shows you what bytecode was actually generated. And that is it for the compiler part of the Python virtual machine. So once we have this bytecode generated, now it's actually the matter of going ahead and running it. So the Python virtual machine is basically a C program with a giant switch case statement. So we look at the opcodes like we saw from earlier, like load const, binary add, that sort of thing. And for every single one of those opcodes, there's a case in this big switch statement. And it will go over all of the byte codes and repeatedly just run whatever instruction you asked for. And so we can take a look at how this is going to run our example. So to give you some background knowledge on this, the black stuff is what comes wrapped in the code. The code has like certain tables in it, like what names it's going to use, what the constants are. And then the blue part is the state of the interpreter. So the interpreter will hold the locals for your current function. It'll hold the globals that are valid all across your Python program. And then there's the stack we talked about, because Python is a stack-based virtual machine. So if we look at, for example, x equals hello, which the instructions were a load const of hello and then a store name of x, what's going to happen is, first of all, we can go look at what the load const instruction is doing in the interpreter. The argument to load const is 0, which means load the 0th constant. And if we look at our constants table, the 0th argument is the string hello. Then it takes that value and it pushes it onto the stack. So we take that hello from the constant table in the code, and then we push it onto the stack. So now our stack just has the string hello on it. So immediately after this, it's going to do a store name, again with the argument 0. And now what that does is it takes the 0th name, which in this case is x, it pops the value off of the stack, it takes the locals dictionary that we have here, and then it sets the name to whatever value we just popped off. So now the locals dictionary has the name x, which was the 0th name, stored at what was on the top of the stack, which was the string hello. So now our locals dictionary has x mapped to hello. So if we look at the next piece of code, y equals world, that's going to be very similar. It's going to basically do a load const, which push the world second. If you look at the argument, this is the first constant. So if we look at our constant table, 0, 1, it pushes the first constant, which is world, into the stack. And then next, when we do our store name, it's going to look at the first name, which is print. It's going to go to the locals again, and then set that name, which is y, to world. So now in our locals dictionary, we have x mapped to hello and y mapped to space world. So now it's going to be the interesting piece of code, which is print x plus y. Now this upfront is going to do 3 load names. First, the second name, which is print, then the 0th name, which is x, then the first name, which is y. And we're going to take a look at what load name does, which is, for example, in the first one, we want the second name print. So it goes and looks at the name print. It grabs the name, and then first it does a lookup in the locals. But obviously, print is not defined in our function anywhere. Instead, if it returns null from the locals, it's going to go up and look it in the globals. And in there, we find print. And then, as you can see, once it finds the value, it just pushes it on top of the stack. So we got the print function from the globals out onto the stack. And next, we're going to load x and y. So for x, which is the 0th name, we are going to look up in the locals, and we're actually going to be able to find x in the locals. So it looks up the name. Okay, it says it's the string hello, and then it puts that onto the stack. Same thing for y. That's the first name, so we go look it up in the locals. We find y has the value world, and we push it on top of the stack. So next, we have the binary add operator. And as we see, it's going to pop off the right operand, then the left operand, and then do an add on it with the left and right. So the right, in this case, is the world string, hello is the left string, and add on strings is defined to be string concatenation. So when we finish with this, it's going to have popped them off and then push the result, which is the sum, onto the stack. So now our stack looks like print, and then it has the concatenated string hello world on top. So now the next function we're going to do, the next opcode we're going to execute is call function with the argument 1. And the argument to call function is how many arguments from the top of the stack you actually want to use. So when we run this, what's going to happen is it's going to pop. The code isn't here because call function has like a pretty complex implementation, but basically you can think of it as popping off the arguments and then popping off the function and then just calling the function with the arguments. So once we run that last bit of code, it's going to give us hello world. And that's basically what happens when you actually run a hello world program like that in Python. It goes through the compiler, it gets turned into that bytecode, and then that bytecode gets run on the Python virtual machine like that, with its globals, its stack, all of that stuff. Thank you, that's the end of the talk. In here, I've left links just in case you're interested, because this was a very high level view. There's things like, how is the print function actually implemented? It turns out it's written in C for performance, and same thing with the string concatenation. Those things are not actually implemented in Python, they're implemented in C. That gets called by the interpreter. And you can also look at, for example, how the peg parser takes that grammar file I showed and actually turns it into a parser that can take those stream of tokens and like do stuff on it. And with that, the talk is over, and I'll take any of your questions.
Yeah, so you said before that other programming languages could also target the Python virtual machine. So using those modules that you talked about before, could you basically would pass that the same instruction set or whatever into like some Python-M module, or would it be some other route to actually like make use of the virtual machine?
Right. So for that, in order to do that, basically there's a mode in Python that lets you run compiled files. If you've ever used Python, sometimes it generates these PYC files, which are the compiled bytecode. So you would write a tool that basically takes your source language, like Java, for example, compiles it into those PYC files, and then that is what will get run on the Python virtual machine. Right.
How does multi-threading work in Python?
Yeah, so that's a good question. So that big loop that we saw for the interpreter, this part is actually being run on multiple threads, and essentially each thread will have its own one of these big switch statements, and each thread will be able to go and edit the globals and stuff. In Python, threading sort of doesn't work, depending on what you mean, because Python does have one native thread for every Python thread, but there are no fine-grained blocks. So only one piece of Python code can hold the lock at a time and run through this switch statement. But for example, if you have a thread that's blocked on I/O, it can give control over to another Python thread, and it can go through this big switch statement. So each Python thread is a native thread, but really only one thread can be executing Python code at a time.
I guess this is also similar to my last question. Hypothetically, if you wanted to pass in, let's say you don't want to have to deal with your own optimizations and you want to use Python's optimizer instead, could you basically pass in your own AST and then have Python? I know it doesn't do many optimizations, but could you go through, rather than the last route to target Python, one route above that where you're passing in a tree itself and then letting Python do the rest?
Yeah, so you definitely can. So let me show you the AST module real quick. So there is actually a function in here that will let you take in an AST, and then it'll run the optimizations for you. So the AST module is actually pretty full-fledged. You can it can not only just parse source code, it can also do transformations and stuff on it. And there is a function that will let you take your own AST and run all of Python's normal stuff on it.
Does Python optimize the bytecode itself? For example, instead of making a function call, it can inline the function call because it's small.
So yes, it does do optimizations like that. Function calls it can't do. It can't do inlining because Python is so dynamic that a function call cannot necessarily be inline and behave exactly the same as the original program. There's no like concept of like pure functions, and there's no way to determine if a function is pure. Like even if you're just adding to a number, it could be the case that your custom class implements numbers in like a completely different way. So it can't do many optimizations, but for example, if you have an if statement that's like if true, then the bytecode optimizer will just get rid of that condition and just put in the body of the if statement right there. Go ahead.
Yeah, so this question is going to be more based on like my ignorance of sort of the difference between interpreted languages and compiled languages.
Yeah,
but since you mentioned that Python still essentially goes through, well, at least C Python still goes through a compiler and generates a bytecode, and then have the Python virtual machine, C Python virtual machine run that bytecode. As far as I'm concerned, for C, for example, I'm pretty sure like a bytecode still gets generated during when it's compiled. So is the difference between interpreted and compiled language just the difference of whether this bytecode is run on a virtual machine or not? Or?
Yeah, so there's sort of compiled and interpreted language are sort of a spectrum. On the fully interpreted side, you would have something like where you literally take like the raw text, you parse it, and then you run that. And those are very rare. There are like basic interpreter, for example, that run exactly like that, but that's very rare these days. And then on the exact opposite, on the compiled end, you'd have something like LLVM, which is taking C code and then turning it into machine code for your computer. And so the interpreter, the compiler, you can basically think of as sort of like exactly what Python is doing, but instead of at the end generating Python virtual machine code, it's generating machine code. And so, yeah, the distinction is sort of like kind of hazy, but the interpreter is generally what we call something that doesn't necessarily have like a physical machine to run on, but has to be run by another program. Whereas if it was running on like a native processor, we'd consider it like a compiled language. And it gets even blurrier with stuff like Java, because Java will first compile a new Java bytecode and then interpret that. But as it's interpreting, it will like keep traces of like, hey, this function is being called a lot, and it's always called with like these few arguments. So let's take that piece of code and JIT it. So just in time compile that as we know that it's important, and then it will generate machine code just for that piece of code. So there's sort of like a big spectrum between like how interpreted and how compiled you are in programming languages.
Final last question, but so like as of the last few years, the typing module has become a little bit more used, more popular in a sense.
Mm-hmm.
So would the typing module, whenever it's checking for some types, because you can't have it like actually throw exceptions when types are mismatched, would that be running on when the AST is compiled, because that's when basically types will start showing up, or is that actually running during program execution through the virtual machine?
Yeah, so the bytecode has no type annotations at all in Python, and that's true in most languages. Basically, you only check types at compile time, and at runtime you discard all type information, you don't care about it. And it's the same case for Python. In Python, actually, the compiler itself does not have the type checker. You have to use tools like MyPy or PyLance, which are these external type checkers. And in Python, basically the same thing is happening, where you have the code is compiled and type checked once, and then at runtime, the bytecode does not carry any typing information with it.
So then, can't you like check if an object is an instance of a class?
Yeah, so the objects themselves are tagged with their types. So theoretically, you could take the compile time like type annotations, store them, and like pull them back up in runtime, and then check if the types are what you expect. And actually, some libraries do that. So let me show you a quick example. There's a library called Pydantic. And what it does is you can have these classes where for example, you have id:int. So the id:int is a type annotation. And what this library is doing is it's taking the AST, taking out the type annotation to figure out how it should build this class. So this class's constructor will only take an integer for the ID argument, for example. It will do that type checking at runtime, but Python itself has no built-in support for that. These libraries that do fancy stuff like this have to get the type annotations and get them at runtime in like fancy ways.
I read this somewhere else. So what is the global interpreter lock?
Yeah, so the global interpreter lock is what I was talking about with the threads. That basically is the thing that shuts out every other thread from touching like the globals dictionary, the locals dictionary, those sort of things. So really only one piece of Python code executes at one time.
So do you think it's possible for it to not do that?
Yes, there have been projects to remove the global interpreter lock. It's called the GIL for short. But the problem with removing the GIL is a lot of Python code sort of has the expectation that it won't be interrupted midway. So a lot of the times people will write Python code that like assumes, okay, if I'm like assigning to a dictionary, then this will always succeed and it will always be like consistent. Because they've used the GIL for so long. In order to remove it, you would have to put in fine-grained locks. So for example, you could have multiple things executing Python, but for example, if two of them want to access the globals dictionary, then you'd want to make sure that, first of all, if both of them go into the dictionary, if one of them's modifying it, is the other one gonna like mess up its iteration while it got modified underneath? So you need like locking there. And you need to put those locks in like all these little places where the interpreter acts as its state in order to remove it.
How does that cause problems when you do like bindings to other languages? Like let's say you have a high performance thing in C++, and you want Python interface to it.
Oh, actually, so when you do bindings, that's the ideal time for the GIL because when you write like a C Python extension, so for example, if you want to do bindings to like a native library, you can release the GIL when you're not accessing Python stuff. So for example, if you're about to do a long like math computation and like some C code, then you can just go ahead and release the global interpreter lock, and that will let other Python code run while your native library executes. So actually those tend to help with Python performance. I've heard it.
Yeah. The same would be true for like file layer or something.
Yeah, exactly. When the interpreter gets blocked on something like I/O network, that sort of thing, it will release the global interpreter lock so that other Python threads can like start to do work during that time.
And so to start a thread, isn't just the async IO library, or is it
It's the threading library.
So how is async IO different from this underlying against runtime?
Sorry, what was that?
How is async IO's runtime different from?
Right. So async IO is an event loop, which actually does not have multiple threads. If you know like Node.js or one of these other popular event loop languages, they all run on one thread. And this one thread, basically what it's doing is it has like these lists of callbacks and works to do. And if something that's like blocked on IO, it'll pop off the next thing to do and just operate that on the same thread. So async IO has a single thread. You can start up multiple event loops, which each run on their own independent thread, but in general, one async IO like reactor will run on one thread and just respond to events on that one thread.
But what about contributing to CPython? Can you maybe talk a little bit about that?
What if you're what?
Contributing to CPython?
Oh, okay, yeah. I didn't really prepare slides for that part, but I'll put some resources in the Discord. Basically, Python has this pretty good developer's guide that teaches you like how to actually like download the source code, how to build the project, that sort of thing. And within this guide, there's also like a link to the bug tracker and like how to find like easy issues to triage. What I would recommend is if you want to tinker with Python, go ahead and go through this guide, and then basically you can try to find an easy bug to handle. You can feel free to ping me on Discord if you find something and you like need help like trying to figure out what to do with it. You can try adding like things to the language. You can change out the grammar a little and play with it there. But if you really want to help contribute back to the language, the best thing to do is sort of triage the bugs, see if they're like still active on the latest version, and kind of review code that other people have written and send out fixes yourself. Yeah, and if you need help in like any of that, feel free to ping me on Discord.
Yeah, I'm not sure if you mentioned this, but what's your role like, in terms of the entire Python like, development community?
So most of my work recently has been in improving the error messages that Python generates. So before we kind of had like these. So before, Python had this problem where, for example, if you had this error, it would say none type object has no attribute X. But there's like multiple X's on this line. I don't know which one it's complaining about that it's none. So a lot of my work in the last couple of months has been, hey, how do we actually like surface this information to the user? So nowadays, what happens is every piece of bytecode that the compiler generates has the column and the line information from the AST and the tokenizer. So now when we're about to throw an error, we can actually go back and look at exactly what like part of the code threw that error. And we can point that out with like these carrots to really like help like newbies and like people find these like tricky errors. So a lot of my current work has been in the compiler and like AST front. Before that, I did a fair bit of work on like the networking and like sockets area. Yeah, I kind of just help around where I can. Yeah.
It's more about Python implementations in general. But given that CPython is the most prominent interpretation out there, when would you want to use other implementations?
Yeah, so if you have mostly like Python code and you kind of care about performance, PyPy is a great implementation. So PyPy is a JITted interpreter for Python, meaning just like Java, it runs your program and then at runtime it tries to figure out, hey, how can I optimize these functions? And that will usually get you like a 50 to 60% performance boost. But the catch is, like I said, Python really has a lot of native libraries like, machine learning and these sort of things. Those won't necessarily work with PyPy out of the box. So PyPy is great if you have mostly Python code, but its compatibility with like the C-based extensions isn't that great. Jython is currently used by an NSA reverse engineering tool called Kedra, because most of their code is written in Java and they wanted to give like a Python scripting layer. So for example, if you're writing in C# or Java and you want to give like your users the ability to script your program, you might consider like Jython or IronPython. But for most compatibility and all right performance, CPython is probably the way to go. Cool. All right then. Thank you, everyone.